would have if the function has an inverse? What important test does the graph of a function pass if the function is going to have an inverse? It was the horizontal line test. It'll pass the vertical line test if it's a function, but in order to be a one-to-one function so that it has an inverse, it also has to pass the horizontal line test. So these graphs of inverse functions, in particular, I want to redraw the graph of f of x equals 2 to the x, just a few key points. I won't take as much time with it, but f of x equals 2 to the x. The graph looks something like this. If I go 1, 2, negative 1, negative 2, 1, 2, 3, 4, negative 1, negative 2, and actually 3. Well, I probably don't need those out that way. F of x equals 2 to the x. 2 to the 0 power equals 1. 2 to the first power equals 2. And 2 to the second power equals 4. 2 squared equals 4. What's 2 to the power of negative 1? 1/2. It's 1 over 2, so it's 1/2. And 2 to the power of negative 2 equals 1/4. So the graph looks like this, really close to the x-axis there. I probably should not draw it in such a way that it looks like it actually crosses the x-axis, so maybe I'll tweak my x-axis like that. So this is the graph of f of x equals 2 to the x. It's an increasing function. It passes the horizontal line test, so it's a one-to-one function, so it has an inverse. The task at hand is to find the inverse. So step 1 in the process, when we're finding the inverse of a one-to-one function, we replace, and we have to think back to section 2.9 because this has been a little while. It's 4 steps in the process. We replace the f of x with the letter y. And we write y equals 2 to the x. Easy step, just notation. That's step 1. Step 2, we actually need to write an equation that the inverse function will satisfy. So that if we were to graph it, we would actually get the graph of the inverse function. So 2, we interchange the x and y coordinates. X equals 2 to the y power. Now as I'm doing this, it occurs to me that sometimes GeoGebra, where unlike the graphing calculator that we use, sometimes GeoGebra will graph a function if it's not solved explicitly for y. And that kind of speeds the process of sketching graphs sometimes. So it shouldn't have any trouble with y equals 2 to the power of x. It graphs that pretty quickly. If we're wondering what the inverse of that would look like, it might say, I don't know, but got to find out sometime, so I'm going to find out now. It might sketch the graph of x equals 2 to the power of y. Who thinks it will? Who thinks it won't? Who's like me and has no idea? I'm going to press enter and find out. Oh, okay. Didn't do it. So sad. Please enter a polynomial equation, x and y. So it'll do it with when it's a polynomial, but not an exponential. Okay, we'll get back to that graph in a moment. X equals 2 to the y power. Even though GeoGebra has a hard time graphing this, and the TI-84 would as well, every point on this will be on the graph of the inverse function. It's just that if we want to write this using the inverse function notation, we have to solve it for y so that we can pick up the y and put the f inverse of x notation there. So step 3 is where we have to solve this equation for y. And the trouble is we don't know how to do this. The variable is stuck up in the exponent, and as long as it's up there, we don't really yet have a procedure of getting it out of the exponent. This section, section 4.3, helps us to establish a procedure for getting the variable out of the exponent when we're solving an equation that has a variable in an exponent. So let's see. Suppose x is not just any old unknown. Suppose it's a specific known number, and it's kind of nice as it relates to the base 2. For example, suppose x equals 8. Can we solve the equation 8 equals 2 to the x power? Think of a number that you can raise 2 to get 8. 2 to the third power. X equals 3 works nicely because 2 times 2 times 2 equals 8. So in a situation like that, it's pretty easy to come up with a solution. Here's another nice one. 32 equals 2 to the x power. What's x? 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, right? 5. 5 factors of 2. So x equals 5. Now it's important to observe that the solution is unique in each case. There's only one power to which we can raise the number 2 to get 8 as the answer. If we raise 2 to a higher power than 3, because this is an increasing function, we get an answer greater than 8. 2 to the fourth power is greater than 8. 2 to the fifth power is greater than 8. If we use a power lower than 3, we get a lower number than 8. 2 to the second power is 4. 2 to the first power is 2. So it's the only answer, the only solution to that equation. One more. How about 1/4 equals 2 to the x power? X equals what? X equals -2. 2 to the power of -2. We notice the point on the graph there with the y coordinate of 1/4. The x coordinate is -2. We know that 2 to the -2 power equals 1/4. I said just one more, but I was kidding. How about 0 equals 2 to the x? How far to the left do we have to grow on this graph, 2 to the x, before we get as low as 0? We never quite get there. Keep cutting it at the y coordinate in half each step we take to the left, but we never quite get to 0. So no solution. And one more. Okay, I'm actually telling the truth here. One more, no kidding. -4 equals 2 to the x power. If the graph of this exponential function never goes as low as 0, is it ever going to go as low as -4? No, not by, about -4 units. So I'm going to say, though, no real solution. Turns out there is a way to define, and we'll talk about this soon enough, there's a way to define logarithms so that we can actually represent this, find a solution that's an imaginary number, something that has an I in it. But we're not going to worry about that in this class. So I'm just going to say no real solution. We like to keep our exponential functions with real values and real numbers in their domain. So we're going to treat this just like we would treat this and say no solution for our purposes. So to solve this for y, let's see. There's just one number, just one power to which 2 can be raised to get 8 as the answer. So 3 is the power that 2 can be raised to get 8 as the answer. 5 is the power that 2 can be raised to get 32 as the answer. Let's see, -2 is the power that 2 can be raised to get 1/4 as the answer. So I'm going to say it like this. Solve for y. Y is the power of 2 which produces x. It's the power of 2 that when we raise, it's the power that when we raise 2 to that power, we get x as the answer. So it's the power of 2 which produces x. So when we write the inverse function, it's kind of awkward to have to say all that. The unique power of 2 which produces x, or the power of 2 which produces x. So when we write the inverse function notation, f inverse of x equals, when what we mean is that y is the power of 2 which produces x, what we say is log base 2 of x. That's the expression that we use.
To mean what you wrote up there.
To mean what I wrote. This expression right here represents the power, and the best way, the clearest way, if you have any desire whatsoever to understand logarithms, and for at least the next couple or 3 weeks of your life, it's a good idea. Any desire at all to understand logarithms, if you think of them as exponents, if you see a logarithm, think that represents a power. And what power? It's the power that this little subscript, called the base of the logarithm, it's the power that this little subscript can be raised to get this number called the argument of the logarithm, this number x, as the answer. So just with the definition of logarithm, there are some logarithms that we can evaluate, and we will, and then I'll come back to this page and I'm going to complete the graph of the inverse function. Yes?
Is it always the 2?
It's not always the 2. It is in this case because the 2 is what was given. But that base of the exponential function will vary depending on the problem. Sometimes it's 10. That's a special case, and it'll be called a common logarithm when it's base 10. And then one that we'll see that's even more frequently occurring than the common logarithm is the natural logarithm, and the base will be e in that case. We talked a little bit about the natural base e last time. So it could be 2 or something else.
So where the 2 is going to be where your constant is.
Yes, what the number right here, we call it the base of the exponential expression here. That's going to go right here, and we'll call it the base of the logarithm. And those have to match if one is going to be the inverse of the other. So a few logarithms we can evaluate without having to pull out a calculator. We'll see how to evaluate logarithms with the calculator in a moment. But a few we can do without having to use the calculator, so let's do that. Example 1. Let's see, I think I will get back to that. Not just yet, though. Log base 2 of 8. When I write this represents the power, the exponent, that the base 2 can be raised to get 8 as the answer. What number am I thinking of? 3. If you raise 2 to the third power, you get 8 as the answer. So that's the value of that logarithm. Log base 2 of 32 represents the power that 2 can be raised to get 32 as the answer. That's going to be 5. Log base 2 of 1/4 is the power that 2 can be raised to get 1/4 as the answer.
-2.
That's -2. 2 to the power of -2 equals 1 over 2 squared. That's 1/4. Log base 2 of 0. This is the power that 2 can be raised to get 0 as the answer. Yeah, when we're wondering how low does 2 to the x go, it doesn't go as low as 0. So, undefined. And if we're trying to keep our domain and range real, log base 2 of -1/4 is also undefined. 2 to the x doesn't go quite as low as 0, and it certainly doesn't go as low as -4. So this is also undefined. Recall the domain and range of the exponential function and the domain and range of the inverse function. The domain of y, well, let's see, should I go y or f? Let's go f. F of x equals 2 to the x is all real numbers. The exponential function, we can take 2 and raise it to any positive power, any negative power. If we think of the graph of the exponential function, it goes all the way to the left. And although it gets really steep, if the base is greater than 1, it will go all the way to the right. You can take 2 and raise it to any real power at all. Now, 2 to the x only goes almost as low as 0. So you don't get necessarily every real number as the answer. The range of f of x equals 2 to the x is only the positive real numbers. So the domain represents the x coordinates of all the points on the graph of the exponential function, and the range represents the y coordinates of all the points on the graph of the exponential function. When we form the inverse of this, which is the log function, what happens to the domain and range? Oops. F inverse of x equals log base 2 of x. At some point along the way, we interchange the x's and y's. And when we interchange the x's and y's, we interchange the domain and range. So whereas the range of the exponential function was only 0 to positive infinity, what we're seeing here, we try to take the log of 0, it's undefined. We try to take the log of something negative, it's undefined. We can only take the log of positive real numbers. So the domain of the inverse function is the same as the range of the exponential function. Those always have to match. The range of a function is always the same as the domain of its inverse. And what's maybe less obvious, because we haven't seen the graph yet, the range of the inverse function is always the same as the domain of the original. So the range of the logarithm, and your calculator will not show you this. We really do need to look at the GeoGebra graph to make this a little bit clearer. The range of the logarithmic function is equal to the domain of the original exponential function. So consider the graph. I won't do the GeoGebra thing just yet, but consider the graph of the log function. I'm going to say f inverse of x equals log base 2 of x. Well, we've already evaluated this at several numbers in its domain. Let's just sketch this graph by reflecting the graph of y equals 2 to the x about the line y equals x. Hopefully it's something close to a square viewing window. I think it is up there. So let's go with the purple, y equals x. There we go. There's the graph of the line y equals x. So let's take points on the existing graph of the exponential function and interchange their x and y coordinates. So if the point 1, 2 is on the graph of this exponential function, then what point's on the graph of the log function? Would you believe that log base 2 of 2 equals 1? What power can 2 be raised to get 2 as the answer? 2 to the first power, 1. So we get that. The point 2, 4 is on the graph of the exponential function because 2 to the second power equals 4. The point 4, 2, right there, is on the graph of the log function because what? Log base 2 of 4. What power can 2 be raised to get 4 as the answer? 2. So it gives us the point 4, 2. Well, let's see, 0, 1 gives us what point? One, 0. And which one was this? Negative 1, 1/2. That's going to give us the point 1/2, negative 1. Not too tough, right? Just to interchange x and y coordinates and plot the corresponding point. This one was, and still is, negative 2, 1/4. And so that's going to give us the point 1/4, negative 2. Now, before we connect the dots, we want to think about asymptotes. What is the asymptote for the exponential function? As it goes to the left, it approaches what horizontal line?
0.
Y equals 0, x-axis. So that's a horizontal asymptote. So, wow. If you have a graph that has y equals 0 as a horizontal asymptote, and you reflect that graph about the line y equals x, then what's going to be the image of the x-axis about a reflection across the line y equals x? Sometimes I can illustrate it, but I have to be careful. I think I can do this. If I put my elbow on the... No. Put this on the board. I'll hurt myself. If I put my elbow on the x-axis just kind of pivot it and reflect it about the line y equals x, the positive x-axis is going to go where?
Straight up and down?
Straight up and down. That was my intent. Straight up and down.
It'd be the
So this point would go right there. That's the idea. If you're reflecting about the line y equals x. So from there to there. So the y-axis is going to be a vertical asymptote for the log function. So if we connect the dots, it'll look like that. Even if I miss some of the dots by a little bit. But that's basically the idea. That's the graph of the log function. So it goes all the way down to negative infinity, and all it takes its sweet time, if you go far enough to the right, the graph will go above any horizontal line that you can draw, no matter how high.
So the result on your like your log 232, for example, your ordered pair on that is x equals 5 and y would equal 2.
Let's see. Yes, I guess it doesn't show up on this particular graph, but what would that be? On the graph of the exponential function, it would be, well, it would be way up here somewhere.
Right.
A better example, possibly, I mean, just to get visual with it. Suppose we go up here to 3.8. I guess that's as high as it'll let me go, or maybe if I use the integrity writing tool, it may let me go a little bit higher. Yeah, there we go. So 3.8 is going to be about right there. So what we're saying is that 2 to the third power equals 8. Now, if I go out here to the point 8.3, that point's on the graph of the log function, and right there what we're saying is that log base 2 of 8 equals 3. And that gives us the point. See, that's the x coordinate, that's the y coordinate. That's the x, that's the y. Log base 2 of 8 equals 3. Here, on the exponential function, this is the x, and this is the y. So the point 3.8 on the exponential function, the point 8.3 on the log function.
Okay, thank you.
Yeah. Now that kind of leads nicely into the official definition of log function and toggling back and forth in between exponential form and logarithmic form. Zoom in on this just a bit. Just a bit more. There we go. Definition of logarithm, as if we haven't defined it enough already. Is this. Y equals log base A. Little a is the base, x is the argument, and y is the value of the logarithm. Y equals log base A if and only if a raised to the y power equals x. What we have is two different but equivalent ways of saying exactly the same thing, describing exactly the same relationship among these three quantities, a, x, and y. If we say it with a logarithm, what we're saying is y is the power that a can be raised to get x as the answer. If we say it with an exponent, what we're saying is y is the power that a can be raised to get x as the answer. Saying exactly the same thing, just one way involves a logarithm, the other way involves an exponent. If we say it using the logarithm, this is called the logarithmic form of the equation. If we say it using an exponent, it's called the exponential form of the equation. Since the two are equivalent, And since sometimes one is a little easier to work with than the other, particularly when solving an equation, we'd like to be able to go back and forth. If I give you an equation in logarithmic form, I'd like you to be able to put it in exponential form. If I give you an equation in exponential form, I'd like you to be able to put it in logarithmic form. It can be helpful in solving an equation. So log base 5 of 25 equals 2 means what number raised to what power gives you what as the answer? So begin with the base of the logarithm. That's 5. And if you 2 is equal to the logarithm, so 2 should be thought of as an exponent. And then the other number, 25, is the argument of the logarithm. So what we're saying, when I say log base 5 of 25 equals 2, is that 5 to the second power equals 25. 2 is the power that 5 can be raised to get 25 as the answer. Back the other way, we've already seen this one a couple of times, but the base of the exponential expression, the number that's getting raised to a power, is 2. So that's going to be the base of the logarithmic expression, log base 2. Now the next number I would write, because for me personally, even though I've been doing this for a decade or two, it's more challenging for me to go from exponential form to logarithmic form than from logarithmic form to exponential form. So what I do in my head is think, okay, what is the exponent? The exponent is 5, and the exponent must equal the logarithm, because we think of logarithms as exponents. So I'll just put the 5 right there. So the base goes where the base of the logarithm goes. The exponent goes equal to the logarithm, and the number that's left, the 32, must go right there. So what we're saying is 5 is the power that 2 can be raised to get 32 as the answer. All right. Log base 4 of x minus 3 equals 3. The base is 4. We're going to raise 4 to the third power. And we'll get x minus 3 as the answer. What we have here actually is a logarithmic equation. Whenever we have a variable that's in an argument, initially, an argument of a logarithm, it's a logarithmic equation. It's a fairly straightforward solution. Just add 3 to both sides, and x is whatever 4 cubed plus 3 is. Didn't say solve it, but I think we could if we had to. 10 to the power of negative 3 equals 0.001. True or false? Am I correct in saying this? 10 to the negative 3. That equals 1 over 10 cubed, yes? And that is 1/1000th. And 0.001 is another way to write 1/1000th. So it's true. When we write this as a logarithm, it's log, and for the moment I'm going to write base 10, because 10 is what's raised to a power. Log base 10 of what? What are we taking the log of here? Take the log of 1/1000th. And that's equal to the exponent, because logarithms are exponents. So log base 10 of 0.001 equals negative 3. Now on your calculator, you have a button devoted to base 10 logarithms. The LOG. The LOG button. If it happens to be a base 10 logarithm, and you press the LOG button, it will tell you the power that 10 can be raised to get that number as the answer. So here goes. LOG. It doesn't show you the little subscript of 10, but it's there. It's just invisible. Of 0.001. If we're wondering what power 10 can be raised to get 0.001 as the answer, the calculator will tell us it's negative 3. If you raise 10 to the power of negative 3, sure enough, you get 0.001 as the answer. We'll see in the not too distant future Now, depending on the version of the TI-84 Plus that you have, some calculators will have a special feature on there which will enable you to put the subscript. Basically, if you take 10 and press the exponent key, if it gives you a superscript rather than a hat, then you're in business, because you have the log base feature on your calculator. If it gives you the hat, just like it gave me a hat there, then you're not in business. You're like me. You have to use the change of base formula if you want to evaluate log base 2 of some number. But in the interest of full disclosure, while we're on the topic, if you go press the math button, just the math button from the main screen, and scroll down to about number 0. Yours does not say solver. I don't think it says solver, or does it? Does your 0 say solver? Do you have an A and a B below that? If you're at 0 and you press down, do you see an A? I don't, but maybe you do. You see an A? I think that's the log base feature, where it actually enables you to type in the subscript to the base of the logarithm and type in the argument. Not a big deal, as far as I know. I don't think that gives anybody a particular advantage on the test, but we'll see how to do that using the change of base formula, and we'll be able to do that. Log base 8 of 1 equals 0. The base is 8. And the power is 0. If we raise 8 to the 0 power, what should we get? We should get 1. What if that had been a 9 instead of an 8? Do you suppose log base 9 of 1 is also equal to 0? What about log base 10 of 1? If I press the LOG button of 1, that's equal to 0. So for any of the bases that are allowed, basically the base of a logarithm has to be positive, and it cannot equal 1, the same as the bases we use for our exponential functions. Log to any base, any of those bases, of 1 always equals 0. 5, whoops, that's not what I want.
So any base.
Right, for example, log base 9 of 1 equals 0. Log base 13 of 1 equals 0. Because 9 to the 0 equals 1. 13 to the 0 equals 1. That's the reasoning there. 5 to the first power equals 5. The base is 5. The exponent is 1, so we get 1 as the answer. Well, the logarithm's equal to the exponent, so the 1 is out there. So log base 5 of what number equals 1?
5.
So that's going to be a 5. 1 is the power that 5 can be raised to get 5 as the answer. So log base 5 of 5 equals 1. This property says if the base and the argument of the logarithm match, the answer is always 1. For example, log base 9 of 9. What power can 9 be raised to get 9 as the answer? 1. And log base 10 of 10 equals 1. So if we press LOG of 10, since it is a base 10 logarithm, we get 1. And those two properties at the top, they're the ones we just illustrated. Log base A of 1 is always equal to 0, and if the bases match, log base A of A is always equal to 1. I think I touched on just about all these properties, these characteristics of exponential and logarithmic functions. I definitely talked about the domain and the range of the log function. It would make sense that since 0, 1 is the y-intercept of an exponential function, 1, 0 is going to be the x-intercept of a log function. And we mentioned the asymptotes. The exponential function has the x-axis as a horizontal asymptote. The log function has the y-axis as a vertical asymptote. Now these buttons on the calculator. We've seen the base 10 button. Let's see, zoom out a bit so we can see the whole thing here. The number e, 2.718281828, and then some, an irrational natural base, does occur frequently in applications of these exponential functions as they relate to exponential growth, exponential decay, as we'll see in a later section. Base e logarithms, let me skip that paragraph, base e logarithms are called natural logarithms, and we use ln to denote natural logarithms. And base 10 logarithms are called common logarithms, and we'll use base 10 to denote those. When we don't write the base, when we just write log of x, it's understood to be base 10. Right, log of x. This means log base 10 of x. And probably I should put that right there. When we write ln, and I'll try to use script there, because when I write that either looks like a 1n or in, so I'll try to use lowercase ln in cursive there. Ln of x, this equals log base e of x. That's what that means. It's the power that the number e can be raised to get x as the answer. So just a calculator button punching exercise here in example 3. Natural log of 20 is about 3, I think. It's the power that the number e can be raised to. Notice the ln button on the calculator. The power that the number e can be raised to get 20 as the answer. So it's going to tell us 2.9957, basically meaning that if we take this number 2.718281828, and that's nice enough place to round it as any, and we raise this to the third power, or let's say 2.995732274, we get a number close to 20 as the answer. Okay, that's close enough to 20, I guess. So that's basically what it's telling us. It's the power that e can be raised to get 20 as the answer. So I guess I should go with 2.9957. I'm going to record this 2.9957. Now, log of 20, if we're going to skip to that just for the basis of comparison, 10 is bigger number than e. It's greater than e by a good margin. It's almost 4 times as great as the number e. So 10 doesn't have to be raised nearly to as great a number to get 20 as the answer than e does. E has to be almost cubed. But 10, if we cube 10, we get 1,000. If we square 10, we get 100. So 10 can be raised to a considerably lower number to get 20 as the answer. Well, how low might that be? 10 can be raised to the 1.301 power. And that'll give us 20 as the answer. If I take 10 and raise it to the power of 1.301029996, that should give us something really close to 20. Yeah, really close to 20. So a smaller power for 10 than is required for e, because 10 is a bigger number than e. So this is about 1.301, I think it was.
How many decimals?
Oh, I didn't really specify here, so it's kind of up to the instructor's mood in this case. So I didn't leave very specific directions for that. So let's go with 4, I guess, if I'm being consistent. So let's tack on, I guess the next one would be a 0. 1.3010. Natural log of e. We're wondering what power can e be raised to get e as the answer. What do you think? What power can e, remember where e was on the calculator on the divided by button? If you press second and then the divided by button, that's the wrong button. Second and then the divided by button, that'll give you an e. What power can e be raised to get e as the answer? E to the first power, maybe? Should be equal to e. So natural log of e is 1. Now the parallel for that would be what we saw a while ago, log, the common log of 10 equals 1 because the base is 10. What power can 10 be raised to get 100 as the answer? 10 raised to the second power equals 100. So if I press log of 100, that should equal 2. What power can 10 be raised to get 1,000 as the answer? 3. What power can 10 be raised to get 1 million as the answer? You're thinking 6. And what power can 10 be raised to get this number as the answer? What is it? 1,000, million, billion, trillion, quadrillion, quintillion. What power can 10 be raised to get 1 quintillion as the answer? Hopefully it's a multiple of 3, or else I'll have miscounted the zeros. Yeah, 10 to the 18th power equals 1 quintillion. All right. Domain and range and vertical asymptote of a log function. We talked about domain and range and horizontal asymptote of some transformations of exponential functions. Let's see if we can figure the domain and range and vertical asymptote of some transformations of log functions. Natural log of 5 minus x. We don't have to look at the graph to figure out the domain, but I think it would be good to look at the graph in conjunction with finding the domain, just so we feel better about it. I don't think I would recommend looking at the graph at all to find the range, because the calculator is very deceptive. The picture that it gives you makes it look like the range is maybe from -2 to 2, when actually the range of each of these log functions is going to be negative infinity all the way down to positive infinity all the way up. You can't see the all the way down part because there's a vertical asymptote right next to where the graph goes all the way down. And there are only so many points the calculator can plot, so it just cuts it off and it looks like it stops. You can't see the all the way up part because these log functions increase very slowly. The farther you go to the right, the more slowly, or right or left, I guess in this case it could be left, the more slowly that the graphs rise. And so it takes a long, long time to see them go as high as you actually expect them to go. But you just have to know, based on what we did, since the domain of the exponential functions is all real numbers, the range of the log functions is going to be all real numbers. Don't let the calculator lie to you. That's just the way it is. So let's see if we can do the I don't remember if I snipped that or not. Yes, I did. Let's see if we can find the domain without looking at the graph. Then we'll look at the graph, and then we'll see what the range is. So maybe the vertical asymptote as well. The domain. What we do is we take the argument of the log, and we know that it can't be negative and it can't be 0. It has to be positive. So if I'm going to write a mathematical statement that says 5 minus x has to be positive, what would I write? 5 minus x has to be positive. Is that one way to write it? 5 minus x is greater than 0. Solve the inequality. Subtract 5, subtract 5. negative x is greater than negative 5. And then, careful, when we divide both sides by negative 1, what happens?
Put the sign.
Make it less than. X is less than 5. So a number like 4 would make the argument positive. 5 minus 4 is positive. 3 would be okay. 5 minus 3 is a positive number. 6 would not be good. 5 minus 6 is negative 1, and we're not taking the log of negative 1. So x has to be less than 5, so the domain is negative infinity to 5. Quick peek at the graph. We'll look at the graph here, and then the GeoGebra graph will be a little bit more telling, but still it will have its shortcomings. Y equals the natural log, just use the ln button there. Still haven't gotten to the change of base formula, so it's good that this is a natural log. Natural log of 5 minus x, and I think the standard viewing window will tell us what we need to know. So zoom 6. Zoom 6. From the graph, does it look like there are only points to the left of x equals 5? No points at 5, no points to the right of 5, only points to the left of x equals 5. If you're wondering where the vertical asymptote is, a couple ways of figuring that out. One way is to walk through the process of doing the transformation. So I would sketch a rough graph of y equals, I'll sketch this in the space and then I'll erase it, or maybe I won't. Y equals e to the x, y equals the natural log of x. This kind of resembles the graph of y equals log base 2 of x that we sketched, the red graph. Careful, I'm going to scroll up, so if it makes you dizzy, close your eyes for a second. Okay, you can open them now. Y equals the red graph there. This was y equals log base 2 of x. Well, y equals log base e of x is going to be a little flatter here and a little steeper there. But basically it's the same picture. So if you're just looking for a rough sketch to answer a question about the domain or range, okay, it's going to scroll back down. So here goes. If the graph basically looks like this, maybe you could, maybe I should have made it a little bit flatter. Something like that. You could put the point 1, 0 on there for reference. That's the x-intercept. But basically the graph looks something like that. Now, if we substitute, and this is a little tricky, if we substitute x plus 5 for x, what would that do to the graph? You're wondering why I'm doing that, but there's method to my madness. 5 units to the left. So the point 1, 0 would go to the point negative 4, 0, like that. And the vertical asymptote, which is the y-axis, would also get shifted 5 units to the left. And the graph would look like that. Shifting 5 units to the left. So new vertical asymptote, x equals negative 5. What if then we substituted negative x for x? Is that equivalent to what we have there? Negative x plus 5 is equivalent to 5 minus x. Everybody believe that? If you substitute negative x for x, wherever you see an x on the right-hand side for a function, what does it do to the graph? It's a reflection about the y-axis. Changes the signs of all the x coordinates. Positive x has become negative, negative x has become positive, so it reflects it about the y-axis. So the graph ends up with x equals negative 5 for the vertical asymptote, negative 4 for an x-intercept, and looking kind of like that. And I think that's kind of the graph that we saw. Now what it didn't show us was the vertical asymptote. The vertical asymptote, here's a good rule of thumb. For these log functions, the vertical asymptote always happens at the endpoint of the domain. So the domain's easy enough to figure out. We just solved the inequality 5 minus x is greater than 0, and we found that it was negative infinity to 5. Well, close to 5, 4.99999 is going to go really low. Second calc, whoops, turn that off. Second calc value, 4.9. Okay, maybe not that low. 4.99. Well, that's a little bit lower. 4.9999999. Okay, negative 18. All right, it's down below there. So the closer it gets to 5, the lower the graph goes. And you tell me how low you want it to go. I can calculate how close it has to be to 5 to make it go that low. So right at the end point of the domain, that's where the vertical asymptote is. So the vertical asymptote is, so the domain is that, vertical asymptote x equals negative 5, and the range, we knew from the beginning that it was all the way up and all the way down. Again, if you're looking at your calculator will lie to you. This looks like the range is from negative 2 to positive 2. Ask how low does the graph go? About negative 2. How high does it go? Maybe positive 2. But actually, if we go farther to the left, we can make it go higher. And if we could see what's going on really close to 5, we can make it go lower. GeoGebra will display this graph a little bit better. If let me just delete this one. If I graph y equals the natural log of 5 minus x, please graph it for me. There we go. You can see the vertical asymptote a little bit better. And if I, let's see, is zooming out the right thing to do, maybe? Zoom out. There you go. You can see what the graphing calculator doesn't exactly want to show you. I can zoom out enough. You can see the GeoGebra even will have a lowest point on the graph, but there's not a lowest point. It goes all the way down to negative infinity. Get more. There we go. There's the vertical asymptote, x equals negative 5. So for always, the vertical asymptote is at the endpoints of the domain. And the endpoint of the domain is x equals 5. Paste this again. This time, let's look at the b part. G of x equals base 10 log of x plus 3 plus 4. When we don't write the base for log logarithms, it's understood to be base 10. So the domain, all that determines the domain is all that's in the argument of the logarithm. So x plus 3 has to be positive. If it is, x is in the domain. If it's not, x is not in the domain. So what numbers make x plus 3 positive? X plus 3 greater than 0. Solve the inequality. Well, you got it, though. So x has to be greater than negative 3. We don't flip the inequality symbol here since we're just subtracting, not dividing. X has to be greater than negative 3. So the domain is negative 3 to positive infinity. What is the vertical asymptote? What's at the end point of the domain? Negative 3. So x equals negative 3 is the vertical asymptote. And the graph, we'll look at the graph in a moment. The range, we just kind of have to know. The graph goes all the way down and all the way up. So negative infinity to positive infinity. On the graphic calculator, y equals log of x plus 3 plus 4. It may not even display the x-intercept. Would you look and say that it goes all the way down to negative infinity? No, it looks like it's about 1 to 4. That's what looks like the range is. GeoGebra should probably do a little bit better job of this. Y equals log of x plus 3 plus 4. Yeah. It does have an x-intercept. It evidently at -3. Would that make sense? -3. Sadly, it's showing natural log. Okay. That's something I have to figure out for GeoGebra later. Back to the calculator. If we go with -3, second calc value, I believe that is undefined there. It's going to go all the way up to, but does not include the -3. So there is a vertical asymptote at x equals -3. If we go 3.01, oops, sorry, negative. Second calc value. -3.01 is not in the domain, is it? How about -2.99? Is that in the domain? Is that greater than -3? Yeah, that works. That's going to be 2. How about -2.999? How about -2.9999999? Each time we tack on another 9, it decreases by 1 more. If you wanted to go to -100, evidently you need about 104 nines after that -2. So it will go as low as you want it to go, just it has to be really close to -3 if you want it to go very low. Okay. And since we haven't done the change in base formula, I'm not going to do part C at this time, and probably never actually. I believe this may still be one of the MyMathLab problems. This continuous compound interest problem, where it asks for the present value and also it asks for the interest rate. So let's find the present value first. That will not require us to solve an exponential equation, but then when it asks for the interest rate, we will have to solve something in the way of an exponential equation for that. But it's not a terribly bad one. So it gives us the PERT formula, and then it takes the PERT formula, A equals P times e to the RT, and solves it for P by dividing both sides. Solves it for P dividing both sides by e to the RT. So what I think I would do if I were doing this is just say, okay, P e to the RT equals A. Divide by e to the RT, divide by e to the RT, and P equals A over e to the RT. Just take the amount that we want it to have that value off in the future somewhere and divide by e to the RT, rather than saying A times e to the negative RT. They're equivalent. If you take this and shove it up to the numerator and change the sign of the exponent, you get an equivalent expression. I just would prefer not to do it that way. I'd rather say present value of that $400,000 is calculated by taking E and raising it to the power of 0.08 times how many years? 20 years. So the annual interest rate is 8%. The number of years is 20 years. So that's the RT multiplied 0.08 by 20. And then if we want it to be worth $400,000, have a face value of $400,000 at the end of that time, take $400,000 and divide by that. Because if we knew how much we had now and wanted it to be worth $400,000, we would multiply by e to the RT to get that. So it's going to be $400,000 divided by e to the power of 0.08 times 20. So, if we have $80,758.61 sitting around that we don't know what to do with, and we want to invest it now, leave it alone for 20 years, and we could find an 8% annual interest rate, then at the end of that time, you would have a face value of $400,000. We could maintain that 8% interest rate with no risk, or limited risk, all the way to there. So $80,758.61.
And to get that E, you do the second divided by.
Yes. Second. Well, it's second LN, second LN button. Second LN. 758.61. Okay, that was not too bad. The B part, I think takes a little bit more work because we're having to solve an equation. Find the interest rate compounded continuously that's needed to have $18,750. So we have $18,750 now, and we want to have $75,000, at least the face value of $75,000, 20 years from now. Basically, I think we're wanting to quadruple it. I think if you take $18,750 and quadruple it, you get $75,000. So we're wondering, how long will it take? No. If we want to quadruple it in 20 years, what would the annual interest rate be to make that happen? So I'm just going to go with, we could use either form of the equation. What if we use the A equals P e to the RT? That's usually the one we use. So we would have $75,000, that's the amount in the account 20 years from now, equals $18,750, that's the amount that we're going to deposit right now, times E to the R times 20. And then we want to solve this equation for R. Step 1, divide both sides by 18,750. We'd like to have, if you want to think of it as a coefficient, I mean, E is really not a variable, but if you want to think of it as the coefficient of that exponential expression, we'd like that coefficient to be 1. We just want 1 times e to the r times 20, not 18,750 e to the r times 20. So 4 equals e to the 20r What we'll do in section 4.5 when we solve this exponential equation is we'll take the natural logarithm of both sides. But there's a property of logarithms that we haven't discussed yet that's going to keep us from doing this at this point. What we do know how to do is to rewrite this in exponential form. Wait, it's in exponential form. What we do know is how to rewrite this in logarithmic form. So what's the base? The base is e. That's what's getting raised to a power. So it's log base e, which at the next step I'll write as ln. That's the natural logarithm. Log base e is the natural logarithm. Log base e of what equals what? The 4 goes here because 4... Gosh, I'm so sorry. It is 4. The logarithm is equal to the exponent. I looked at it and thought 4 was an exponent, but 4 is not an exponent. 20r is the exponent. 20r is equal to the logarithm because 20r is the exponent. So it's the natural log of 4 equals 20r. So once we rewrite it in logarithmic form, it's no longer an exponential equation. In fact, it's not even a logarithmic equation. It's a linear equation because it's just 20 times r equals ln of 4. So we can divide both sides by 20. And r equals the natural log of 4 divided by 20. Careful when punching this up on a calculator. It's very important that when you take the natural log of 4 that you close the parentheses after that 4. Natural log of 4 and then close the parentheses like that. If you don't, what it'll do is divide 4 by 20 and then take the log of that. You want to take the natural log of 4 and then divide that by 20, and when it does, 0.06931. Now let's see how many decimal places it wants in the final answer. Round the final answer to 4 decimal places, and then round all intermediate values to 2 decimal places. What I think is we need the intermediate value. I would say the intermediate value should be 0.0693, but the final answer should be 6.93%. So I'm not sure what they meant by the distinction between final and intermediate, but it's going to want 6.93% for the final answer. So it would take almost a 7% interest rate to quadruple an amount of money in 20 years.